Welcome back. In this lesson, we tackle one of the most powerful and most misunderstood tools in endpoint security: certificates and the public key infrastructure behind them. By the end, you'll understand asymmetric keys, what an X.509 certificate really is, how a PKI hierarchy builds a chain of trust, and how to deploy and troubleshoot certificates on real endpoints using certutil and Intune. Everything starts with asymmetric cryptography. Instead of one shared secret, you have a key pair, a private key that stays secret and never leaves the holder, and a public key that you hand out freely. The two are mathematically linked, but you cannot derive the private key from the public one. That asymmetry is the foundation of every certificate we'll touch today, so hold on to it. Now, the single most important distinction. Signing and encryption use the key pair in opposite directions. To sign, you use your own private key, and anyone can verify with your public key. That proves the message came from you and wasn't tampered with. To encrypt to someone, you use their public key, and only their private key can decrypt it. Get this direction right and half of PKI suddenly makes sense. So what actually is a certificate? It's a public key bundled with identity claims, all signed by a certificate authority, ACA. The format is X.509. You'll read the same fields over and over: the subject, which is who it identifies, the issuer, the CA that signed it, the validity dates, the public key itself. And two you must know well: the subject alternative name, the SAN, which carries the real identity for TLS and 802.1x, and the enhanced key usage, the EKU, which says what the certificate is allowed to do. Real PKI is tiered for safety. At the top sits the root CA, which is self-signed and is the ultimate trust anchor. Crucially, after it signs your issuing CS, the root is taken offline, powered off or air-gapped, because if its private key is ever stolen, the entire infrastructure collapses. The online issuing, or subordinate, CA then does all the everyday signing. If that issuing CA is compromised, the root can revoke it and you reissue, which contains the damage. Validation works by building a chain. The endpoint takes the leaf certificate, finds its issuer, finds that issuer's issuer, and walks up until it reaches a self-signed root. That root must already be trusted, sitting in the local machine root store. The intermediate issuing CA is usually supplied in the chain or fetched via the AIA extension. To check all of this from a Windows endpoint, certutil-verify-urlfetch builds the chain, fetches revocation data, and tells you exactly where it breaks. Certificates have a lifecycle. They begin with a certificate signing request, a CSR. The device generates a key pair, keeps the private key, and sends only the public key and subject to the CA. The CA issues against a template, and the cert is installed. Auto-enrollment quietly renews it before the not after date. And when a certificate must be killed early, it's revoked. Relying parties learn that either from a periodically published certificate revocation list, the CRL, or from a live OCSP lookup. How do certs actually land on endpoints? Domain-joined devices use a DCS auto-enrollment, driven by certificate templates and group policy. For Intune managed or cloud devices, you pick between two profiles. ASCEP profile has the device generate its own key and send a CSR through the NDES connector, so the private key never leaves the endpoint, which is perfect for device authentication. A PKCS profile generates the key centrally and imports it, which suits user S/MIME where the same key must be reused. And a separate trusted root profile pushes out the anchor. Why go to all this trouble? Because certificates power so much of the secure endpoint. They authenticate devices onto the network with 802.1x over Wi-Fi and wired. They authenticate VPN connections without a password to phish. They prove server identity in TLS, sign, and encrypt email with S/MIME, and sign code so it can be trusted. And increasingly they enable certificate-based authentication straight to Microsoft Entra, giving you genuinely phishing-resistant sign-in. When certificate authentication fails, certutil is your scalpel. Certutil-store my lists the machine's own identity certificates and tells you whether the private key is present. Add-user to look at the user store instead, or -enterprise nt-auth to see which CAs are trusted for Entra NAD logon. Certutil-dump decodes every x.509 field of a cert file. And the 4 golden questions to answer every time: is the private key present? Does the chain reach a trusted root? Has it been revoked? And does it carry the right EKU? Let's recap. Asymmetric keys give us signing, with the private key, and encryption, to the public key. Never confuse the two. A certificate is a signed public key plus identity, validated by building a chain from the leaf up to an offline root you trust. SCEP keeps the private key on the device while PKCS escrows it centrally. Your task: in a test tenant, deploy a device certificate to one managed Windows endpoint with an Intune SCEP profile, then prove it works for certificate-based authentication. Use certutil-store my and certutil-verify-urlfetch to capture the subject, SAN, EKU, the full chain, whether the key is present, and the revocation result. Then revoke the cert at the CA, refresh the CRL or OCSP, and document exactly how the endpoint's behavior and certutil's output change. See you in the next lesson.